Hey guys, this was a math question, hopefully with practical application. So, in Australia and many countries, there is a retirement system, right? So, what is going to be the final amount when someone retires? So, they start working at 20, things accumulate, they compound, and retire 65. What is going to be the amount at the retirement? And this has a very serious implication in terms of managing lifestyle and how to survive with that amount of money. So how do we do that using math? So this is what I'm trying to show you. A bit of a disclaimer: this is not a financial advice. Please see a consultant or professional before acting on any of this stuff. The point of this video is to show usability of math to solve practical questions. Okay, so let's make some assumptions and dive a little bit deeper. In Australia, when someone works, government already put 10% of the salary aside each year as a retirement amount, right? So all of that go to a fund, we call it superannuation. And at the end of someone's working life, that is used for giving them allowance or whatever that is. So let's make it this simple using some numbers so we can work out the math. Okay, let's say someone is earning salary. It's $1,000 a year, very very low salary, but we are trying to work out the math, so I'm keeping numbers very simple. All right, so salary 1,000 per year. Okay, and then 10% of that, which is $100, will go to superannuation per year. Okay, so I'm gonna call SA superannuation. Okay, so this accumulation, it is not linear, so it does not mean that you just multiply it by number of years. Every year things compound, so the number will be very, very different. Okay, so it's not linear, it's geometrical. Cool, let's make some assumption then. So let's just say someone starts working at the age of 20 and retires at 65. Standard numbers. That gives you about 45 number of years. So this is going to be the terms when we use formula in math. Okay, so here is 45, that's our term. And let's say the starting superannuation balance is not zero because you have nice parents and they give you $50 to start with. But many times it can be zero, okay? But I wanted to show you a little bit of complexity, so that's why I put starting balance not zero, but some sort of number, arbitrary number. Okay, so this is the balance when the time equals to zero, like time equals to zero before you even start working, and compounding begins. Cool. Let's say your money per year is very generously grows or compounds 10% a year, right? This is a generous number, but we're trying to keep it simple to get the math working. So what that means is 10% per year. It's actually 1.1 because we are adding 10% to the previous amount. So 10%, this is to convert percent to number, and that equals to 1.1. Okay, so you're adding 10% more than what you start with. Okay, cool. And let's say your fixed employer contribution, this is very important. So every year the contribution remains exactly same, and this is 10% of the salary, which in our case we assume it to be 100 per year. Okay, so let's give some variables, name and stuff, labels. So okay, let's call n equals to 45. That's your number of terms that we're gonna try to estimate. Okay, or number of years, for example. Let's call the starting balance as S0. So summation at time equals to 0. Okay, so S0 equals to 50. So make sure that this is readable. S0 and 50 are different. I'll try to keep them separate and legible. Okay, let's call annual growth rate, which is our 10%. Let's call it G. So G is equals to actually 1.1, not 10, just to get the math work. Okay, and then C, capital C, is our constant contribution. That is $100 per year. Okay, cool. So I want to show you this, what this means geographically, so in a graphical manner. So let's draw a graph. Graphs are great. Okay, cool. All right, so we have x and y axis. Okay, this is your x, this is your y, this is the number of terms, correct? So 0 and 45, okay? So 0 age-wise, that is going to be about 20. And 45, it's 65 in terms of age, okay? But we are not going to worry about it, so I'm going to remove it for now. Okay, cool. Let's give some y value, that is your accumulated superannuation amount, okay? So this one is 100, 200, 300, so on. Okay, so here when we start out, our balance is $50 because that's parents' contribution, that's what we start with, okay? And after 1 year of work, right? After 1 year of work, boss is happy and you get $100 more. So you are here and then we get 100 more, okay? But what has happened within the year that this amount has compounded. So what we expect to be here, but actually is little bit higher than what we expect. So a little bit higher than 150. Hope that's clear. Okay, hope that's clear. Okay, so we expect it to be 150, but it's not, a little bit higher. Okay, cool. We work 1 more year and 100 more should be added to your account. So we are here again, right? And we are adding $100 more, so roughly here. But within this 1 year time, the previous amount has compounded. So we're gonna add a little bit higher than what we estimate to be, okay? So just want to show you a difference between what we estimate versus effect of compounding, so on. Okay, so the question remains, and this is the try we are trying to answer that, is what is going to be the amount here at the age of 45? What is y? What is y value at age of 45, right? Not age, sorry, working, no, period 45. So age will be 65. Okay, that is what we're trying to answer. Okay, so let's drive this more systematically and draw some table. Okay, so let's go systematically one by one. So here we have some table data here. I think that's enough space for us to work out math. All right, so we are calling n number of terms, and then this is middle spaces for working, and then here we have total or accumulated superannuation. Okay, so first, or time equals to 0, well, that is no extra contribution because you haven't started working yet, but parents gave $50, right? So our amount at that time is $50. Cool, awesome. Then what happens at the end of 1 year? Okay, so what happens here is we take 1.1, which is our growth rate, we estimate that, right? So whatever is present before, we multiply it by 1.1, our growth rate, right? Plus our supervisor or the boss gave us $100 of superannuation. That's coming like salary, 10% of salary, right? So all of that is 55 plus 100. So that gives us to 155 at the end of first year. Okay, cool. Let's look at second year. So again, the same algorithm works out in a way that we take whatever present at the end of first year, right? That is 155, and we compound by 10 times. So 10%, sorry, not 10 times. So 1.1 times that, right? And then $100 is added. Okay, so that comes to 270.50. Okay, and then third, same algorithm, we have 1.1 times 270.50, and we add 100 again, okay? And that comes to 397 point something, 55. Cool. Now we continue and we want to know what is this value at the end of 45. What is this? Without doing it step by step or like repeatedly doing it 44 times, right? We want to use math as a hopefully shortcut. Okay, cool. So let's break this down. What we need to do is go through each steps and see whether there is a pattern that we can use. Okay. Right. So I'm going to remove some numbers and stuff. Okay, let's clean this out. All right, let's start with first term. Okay, so first term is pretty straightforward, right? We haven't done much. We took the 50 and added 100. Easy. All right, cool. Second one. What has happened here is that 155 is just this, guys, right? Nothing magical there. So what we're going to do is in a different color pen, we're going to expand that and substitute this value with this people. This value. Hope that makes sense. Okay, so let's try that. So equals to 1.1 times substitution plus 100. That's what we're gonna do. The 100 is just the remaining term over there. Cool. All right. Okay. So what is 155 again? Is 1.1 times 50 plus 100. Okay. Now let's expand this this parenthesis. So we're gonna multiply here. So this becomes 1.1 times 1.1. So 1.1 square times 50, correct? And then we're gonna multiply this out. So it will be plus 1.1 times 100. Okay, that's just expansion of the bracket, or multiplication, I should say. Cool. All right, then we still have to add our 100, which is here. Awesome. So basically 1.1 square times 50, 1.1 times 100 plus 100. Okay, and then let's go one more step for the third term. I'm going to change my color. So what we did here is we took whatever the previous amount is, which is 270.5, added 100 bucks. So let's use step substitution again. So we're going to, that is exactly what 270.50 is. And we're going to substitute that here. Okay, same strategy. So 1.1 times the substitution plus 100. Okay, cool. So what do we have? 1.1 square times 50. 1.1 times 100 plus 100. Yep, so that is that 100 coming over here. Awesome. All right, let's simplify this. So that is 1.1 cube now times 50 plus 1.1 square times 100 plus 1.1 times 100, okay, plus 100, right? Cool. Now what we can do is we can write this 100 as 1.1 to the power of 0, because that equals to 1, and 100 times 1 is how 1. So this is just a little math convention which we'll use a little bit later. All right, so what do we have here? So here we have this term, right? And if you notice, what is that? So it's basically whatever we started with. So this S0, our starting amount, it has compounded 3 times, right? So that is why the 3 comes in. So every year it compounds by our fixed number, correct? So that makes sense. So we're going to have a growth rate, which is 1.1, and we compound by n, right, at this stage. Okay, that makes sense. That's cool. What is that? What is that? That looks a bit messy. All right, so let's simplify this. We notice that, that's not a good color. One sec. All right, so what we're gonna do, we're gonna simplify this, okay? So what are we gonna do is we're gonna have 1.1 cube times 50 plus, I'm just going to reorganize it a little bit neater So I'm going to start with the last term here. So 1.1 to the power of 0, no problem, times 100, right? That's just that term. Okay, plus we're going to use this term now, which is 1.1 times 100 plus this term 1.1 square times 100. Okay, now why did I do it? And hopefully that one will make sense very clearly, hopefully very soon. Okay, cool. So when we look here, we see that this 100 is common, right? That is very common. And we also see that this exponential or some constant, it increases by 1, right? So that one, it's similar to something called a geometric series. So very quickly, what this means, very quick primer, okay? We have a sequence and series, okay? So sequence is just a list of numbers, doesn't really matter. So here what you can have, this is not really helping me, what we have 1 times 100, okay? And we are not going to add plus, we're just going to separate that with a comma, so like a second number, who cares? 1.1 to the power of 0, sorry, 1.1 square times 100, and then 1.1 times 100. Okay, these are our terms. Then this will be plus, not plus, sorry, my bad, and comma, this one will go forever. Okay, but when we sum these guys, when we sum the terms of sequence, so we have 1.1 to the 0 times 100 plus the second term 1.1 to the power 1 times 100 plus the third term plus so on, right? And then we're going to have 1.1 to the power of n times 100. This is the general form. This can go forever, okay? So this is a geometric series because if you look at the term number 1, 2, 3, right? If you look at the ratio of those two terms, if you look at S2 divided by S1, so we're going to look at this divided by that, right? Is 1.1 to the power of 1 times 100, correct? Divided by 1.10 times 100, right? So that 100 cancels out, that's just 1. And this one, 1.1 to the 0 is just 1. So the answer is 1.1, okay? Then if we look at, I'm gonna have more colors now. Let's choose purple. Okay, let's look at these two guys, okay? We look at the ratio of those two. So I will clear this, okay? Delete. And let's just write that the ratio are 1.1, okay? That's what we found out. Cool. All right, here. So we're gonna divide this one with that one, okay? So what does that mean is 1.1 square times 100 divided by 1.1 to the power of 1 times 100. 100 cancels out. The answer is also 1.1. So the important thing here is the ratio is always constant. And in our case, that is 1.1, okay? Between terms in a sequence. Okay, cool. So, okay, so basically what I'm trying to say here, that this 100 is constant, as you can see, right? That's a constant, that's good. And then this exponential, that increases by 0, 1, 2, and so on, okay? So this is a geometric series, okay? This is a geometric, okay, with constant. So constant, I'll go in a second. With constants, so constants equals to 100, and the ratio equals to 1.1. Okay, cool. So in our notation, or the way we label variable, this constant is we call C, because that is the fixed contribution from your employer, right? And then in pure math textbook, you will say this term as an A, just coefficient. And the ratio, we call it growth rate. So it's capital G for us, but textbook will probably refer to as R for ratio. That's fine. Beautifully, that this geometric series has a sum. Math has already given us that wonderful tool. So the sum of a geometric series, sum of a geometric series is, so that'll be sum a to the power of something constant ratio to the power of n equals to constant, which is a 1 minus r to the power of n divided by 1 minus r. Okay, so that's a very well known fact. So we're gonna use this in our case. Okay, so let's write this in our label. So a is c, 1 minus r is our growth rate to the power of n, 1 minus growth rate. Okay, that's what this means in our notation. So okay, we're gonna substitute this here up there. So let me just clear some of this thing so we don't need, what I'll do, I'll just remove this. Okay, and then I will move this. It's okay. Okay, so let's write it down. Let's make a, and so here 3, this is where we were. Okay, and we can probably start generalizing it now. So let's call it n for generalize, and we're going to test it a little bit later. What we found that as of n, so sum at the nth term, 45 in our case of interest, but for n, general speaking, we have a growth rate which is 1.1. So we have a growth rate compounded n times, right? So n times compounded. And we have a 50, which is our coefficient, or s of 0, which is our starting term, right? Starting balance or initial balance. So it's not 50, this is S0. Plus, we're gonna have all of these things to deal with. And we know it's a geometric series. So to simplify, we're gonna write that as a series. N equals to something 0 to whatever, n or m, whatever. No, I should not do that. I should probably put a k equals to 0 and to n. So we're gonna have that sum matching up. Okay, cool, not a problem. And then we're gonna have a, which is our constant c, times growth rate times k, right? So we're gonna sum it up from 0 to n, whatever that is. So in first case is 1.1 to the power of 0. That's our first case here. And the second case will be here, and k equals to 2 will be here continuously, right? So we should probably do 0 to n minus 1 because we are only doing twice when this third term. So that should fix it. Okay, cool. All right, cool, awesome, that sounds good. So, and we're gonna simplify that as an equation. So here, okay, let's just start again. S0, g to the power of n, and this sum here is c, right? 1 minus g to the power of n, 1 minus g. Okay, so that's just writing this part equals to that. Cool, all right. Cool, all right, hopefully this is all clear. Makes sense. Cool, all right. So let's test it. Does it even work? Right, using our formula, let's test what we know sums to be. Okay, so hypothesis. I made this way too big. I'm gonna probably squeeze that. Nope, not working. Okay, that's better. Okay, this is our final important sort of step. This is what we derived. Okay, so let's do s of 1 using our equation or formula. okay? Using our formula, okay? So S of 1, what does that mean? So S0, which is 50, right, times 1.1 to the power of 1 plus C constant, which is 100, 1 minus 1.1 to the power of 1 divided by 1 minus 1.1. Okay, we are in luck today because 1 point to the power of 1 is just 1.1, right? So what that means is this term equals to 1. They are exactly same terms. So S1 is 50 times 1.1 plus 100, which is exactly what we shown before. Right? 50 times 1, 155. Correct? This people. Awesome. So that's exactly the same. Checks out. Great. Let's do it for S2. What's happening with... let's keep S2. Let's do S3, okay? We want to make sure we get the right answer with 3. Okay, so third term, correct? So here S0, which is 50 times 1.1, our growth rate times to the power of 3 cube plus 100, 1 minus 1.1 to the power of 3, 1 minus 1.1, okay? Now, what does that mean? So 50 times 1.1 cube, who knows what that is at this stage? All of that, I do have my calculator with me. Okay, so 1 minus 1.1 to the power of cube, right, divided by 1 minus 1.1. That comes to 3.31 times 100, 331, okay? And we're going to add the remaining term, 331 plus 50 times 1.1 to the power 3. Okay, so we get 397.55. Do we have that? Correct, we have that. Okay, so all works out well, beautiful. What does it mean for our final S45, it's our interest, right? So let's do it S of 45. This is what we're dying to find out, which is going to be S0 50 times 1.1 to the power of 45 plus 100, 1 minus 1.1 to the power of 45 divided by 1 minus 1.1. Okay, so I'm just going to plug this number in my calculator and give you just one answer. So that term is 3644 plus 52, and then, okay, cool. And the other one is 100 times 1 minus 1.1 to the power of 45 divided by 1 minus 1.1. Okay, this comes to 71890 plus 848 something. All right, let's add them together. A plus B. All right, so this comes to 75,535.007. Okay, sorry. 00787. Okay, this is as 45. This is what our amount should be if we start with $100 per year compounded 45 terms, plus we had the starting balance of $50 to begin with. Okay, cool. So what does, before we check with the Excel, what does this term mean? What is this? What is all this stuff telling you? Right? What does it mean? So basically what it's telling, it's breaking down the answer into two parts. So one part is very simple. And that's the initial amount, right? The $50 we started with. That one is simply compounded n times with the growth rate we expect, right? So that is just simple sort of compounding. So that is very simple compounding, right? That's what it is. So very simple. That's beautiful. Okay, plus we have this term. So all this extra contribution added over 45 years that is just sum of a geometric series. So what is interesting here that even though we had this sound complex problem, math conveniently broken it down into its um, two parts, two essential parts, right? And that's what the formula shows. So it's actually quite interesting that systematically we can derive this equation that way. Cool. All right. So we can verify our answer as of 45 because I have an Excel file which I have done calculation here. Just 1 second. Uh, Yep. Okay, cool. So this is pretty much the parameters. We set it up as 45 terms. Rest is identical. And the formula is we start with $50 as 0. And then we compound it 10% and add $100. And you can see at the bottom, that's the formula and so on. And numbers matches, right? We got 155 at the first term, 270 for the second term, and so on. And at the end of 45th term, 75535.00787. 75535.00787. There you go, guys. Math works. Excel works too. But more importantly, math works. Okay, so now the question is, when does this equation break? So what is the stress test, or what are the assumptions, here? Okay, so I'm just going to copy that. Copy. Paste. Okay, well, what are the assumptions here? So the strong assumption here is that C, which is fixed contribution, right? So C is always fixed. So what that means is over the whole working life, right? The salary remains 1,000, that's okay. But more importantly, the contribution is always 10%, which is $100 standard, no change over 45 years. So this is a very strong assumption, and it's not going to be true for real life, because normally salary increase over a couple of years, and as people have more experience, they can take more responsibility, climb the ladder, and the salary increases, and with that the contribution will also increase. So this is a very, very strong assumption, and it's probably not going to be a realistic thing. So, but to account for variable contribution, slightly more complex. So we have not done it, but just good to be, cautious. The second thing is growth rate. It's 10%. It's pretty high. We can set it low, but again, similarly, like with stock market and other investment, as people age, the portion of the risky and therefore sometimes high growth asset is decreases with time, because when close to retirement age, we don't want to take risk. We want to be more conservative. So at that time, more and more portion of the money goes to bonds or bank deposit and so on, right? So your growth in the beginning of like 45 years, it might be pretty high, but then it's gonna be slow, right? If I haven't decided right where to frame it or not, graph it, but it's not constant. And in theory, we can take integration or area under curve and then divide that by 45 to get average value. We can do all of that stuff, but that's again something we have to be mindful that it's not a constant rate, it's an average, and it is going to change as well. So again, this is just to get the math sort of work out as a simple assumption, but good to be careful and know our assumptions so we don't break it. Hope this interesting to you and hope that helps, and go math.